What's up, everyone? Here are the solutions for quiz 12. And for this quiz, basically we are exploring Riemann sums, right? So first, I put a problem on here that has just some kind of work with sigma notation. And for the first sum, basically I'm summing up reciprocals of even integers. So this should be sum as I goes from 1 to n. The reciprocal would mean we have to sum 1 over, and when I is 1, I sum up a half, so I need to multiply I by 2. And for the last term, we're not going to go up to n, we're actually going to go up to I equals 10. Right, so that when I is 10, I sum up 1 over 20. That's for the first part. For the second part, now notice these are powers of 2. So I'm summing up reciprocals of powers of 2. So I is going to start at 1. I have 1 over 2 to the I. So that when I is 1, I get 1 half, 1 over 2 to the first. And this is precisely, for the last term, this is going to be precisely the exponent of 2 that gives you 256. And I believe that is 8, if I'm not mistaken. Right? And so that would be the answer for that one. And for the last problem, now we have an alternating sum. So let's see. I start out with 1, which means and notice these are all powers of x. So for the first term, that means I have x to the 0. So I'm going to start my sum at I equals 0, x to the I. I'm going to end my sum at 17, so that the last term is x to the 17th. But in order to make my signs alternating, I have a minus 1 to the I. So when I is 0, that's positive. When I is 1, that's negative. When I is 2, that's positive. When I is 3, that's negative. It does indeed work out that the signs match. So I don't have to have like a negative 1 to the I plus 1. For the second problem now, we're exploring Riemann sums in the context of finding areas under curve. So we have the function x squared, and we want to use rectangular subintervals to find the area from 0 to 1. So now if I break the whole interval into n subintervals, the width is the length of the interval, which is 1, divided by the number of subintervals. So I divide 1 by n. So just to kind of visualize what that looks like, I had you draw just a rough sketch of the function. And we're going from 1 to 2. I'm sorry, we're going from, I guess we're going from 0 to 1 for this one. So that means, oh, I'm sorry, I'm drawing the wrong function here. I'm thinking of a different problem. We're doing x squared from 0 to 1. So it looks like this. And we're splitting this up into n subintervals, just like so. Okay. And if we keep going, okay, for the first subintervals, if we're going to take right endpoints, what's the height of the corresponding rectangle going to be? Okay, well, if I start at 0, the first subinterval is going to be between 0 and 1 over n. So the height, if I take the right endpoint, that means I have to take 1 over n, I evaluate my function at that point, I get f of 1 over n. Similarly, if I take the second subinterval, and
the right endpoint of that happens here for the second arrow, so I plug in 2 over n into f, and that's my answer.
Now if I take the I subinterval in general, it's going to be, the pattern is going to be it's f of I over n, or f of I times 1 over n. So now if I want to write the formula for the area of the ith rectangle, first I need the height of that times the width, so it's going to be f of I over n times the width is just 1 over n because that's the width of every subinterval. So if I plug this into my function, which is x squared, it's going to be I squared divided by n cubed, just like so. Excuse me. Now using sigma notation, I can sum up the areas of all these rectangles. So that would be the sum. I goes from 1 to n, since I have n rectangles, right? First, second, third, all the way to the nth rectangle. And then summing up the areas, so it's f of I over n times 1 over n. And I know what that is from up there. This is the sum. I goes from 1 to n of I squared over n squared. And at the beginning of the quiz I provided some closed form formulas for sum. Since I'm summing up I squared, we're interested in this formula here. So before I do that, I'm sorry, this was n cubed, not n squared. Before I do that, what I'll do is I notice that 1 over n cubed is a constant. I bring that in front of the sum. So I get 1 over n cubed times the sum of I squared as I goes from 1 to n. And now the formula at the beginning of the page started with I at 0, but it doesn't matter because when I sum up 0 squared, I just add 0. It doesn't change anything, so I can still apply it. So I have 1 over n cubed times the closed form is going to be n plus 1, 2n plus 1 over 6. And for the last part of the problem, this is now asking us to compute the limit as n goes to infinity. And basically what I have is a rational function, right? It's a fraction. It's n plus 1, 2n plus 1 over 6n cubed. And when I take the limit of this as n goes to infinity, I'm interested in just the ratio of lead coefficients because the degree on top is 1 plus 1 plus 1 is degree 3, and the degree on the bottom is also 3, so the degrees are equal. And the lead coefficient comes on top when I multiply these three together, so I get 2 times n cubed. So this is going to be the limit as n goes to infinity of the expression on top, but I'm not going to write it. I'll just write the simplified version of 2n cubed over 6n cubed, and that limit is exactly 1 over 3. There you go.